There are two major ways to calculate oxidation number. One of the most standard approaches people use is to simply do it by rote. And if we use the rules, we want to follow through in order. Now, Appendix D of our book will list out rules in a slightly different format than this book has. Any source that you find for the rules, it's going to be an accurate depiction of it. And really, it's all based on electronegativity, which we'll actually see in the video, oxidation number by the structure. But let's take a look right here. So we want to go through in order because really we're starting out with the most high order of our rules. Now if we have an element, it's going to have an oxidation number of 0 when it's in its elemental form. Now remember, that may be a single atom, or it could be some of our more complex elemental forms like S8. And that would be something like sulfur blooms. So in S8, everything would be oxidation number of 0, or O2, also going to be oxidation number of 0. Now if we have an ion, like F minus, that's going to have a -1 oxidation number because that's what the charge is. So the next tier down, we say that hydrogen is always going to be a +1 when it's paired with a nonmetal, or -1 when it's paired with a metal. And the reason for that, remember, hydrogen is totally middle of the road for electronegativity, which means that if it's a nonmetal, it's the weaker electronegativity, and so it ends up with a positive charge. If it's with a metal, it's more electronegative than the metal. It's going to steal the electron and end up with the -1 charge. So that's a little bit of the why that's behind that rule. Now, oxygen, there's only one exception to that one. It's almost always going to be -2. Now, if you do have something like a peroxide, where you've got an oxygen bonded to an oxygen in the middle of a molecule, this could be a hydrogen or the rest of a larger molecule. This could also be a hydrogen or the rest of a larger molecule. But if you have an oxygen single bonded to an oxygen right here in the middle, then each of those are going to have a -1 oxidation number. So that's going to be our only exception to oxygen being a -2. Now, as you get further and further down this table, you start paying less and less attention to these rules because you can start having different oxidation numbers than you expect. Now, if you end up in a case where you don't know and it seems like two rules are conflicting, you go with the higher rule. And we'll see examples of that here in a minute. Now, our group 1 and group 2, those are going to be +1 and +2 ions most of the time. And I say most of the time because remember, it is possible that they're going to start picking up extra electrons and have some sort of a negative oxidation number, really unlikely. Or it could be that they lose more electrons, also pretty unlikely. But we can have some exotic forms where we'd see that happen. Now, when we come around all the way to our halogens, those are usually going to be -1, but sometimes we're going to see halogens have a +7 oxidation number. And there's some other options for those as well. The biggest one is if we have two different halogens attached, though, to a central atom. Suppose we have something like carbon bonded with a fluorine, bonded with a chlorine, and then other things on there too. The more electronegative of these is going to get a -1 for sure, and if the other can't end up -1, then it doesn't. It gets a little more complicated in that scenario. But overall, we're going to sum up the oxidation number of all of the attached atoms of the molecule, and then we're going to subtract whatever our unknown is, and we're going to have to make sure that that adds up to our charge. So if we know a bunch of atoms and there's one that we're not sure about, we figure out what the charge will be, and then we just solve backward for that one. So let's take a look at that here with ethanol. We know that hydrogen is always going to be a +1 when it's bonded to these nonmetals. So each of these will be a +1 oxidation number. Now notice we're going to have an overall effect from the 6 of these of +6. But the actual oxidation number of the atoms in this molecule is going to be +1. Now let's come along here to oxygen. Oxygen is going to be a -2 because it's not in a peroxide. So right now we're at +6 -2. Now we got 2 more carbons. And we're not sure what we're going to do with carbon because it's not one of our rules that we had up above. So let's just go ahead and put in +x equals what the charge of the whole molecule is. Ethanol is a neutral molecule, so my charge will be 0. So we look at this and say, well, 6 -2, I'm at +4, plus something gives me 0. That tells me that I have to be at a -4 for x. That's got to be what's remaining. Now I come back over here and say, let's distribute that among all these carbons. I have 2 carbons shown here. They have to get up to a -4 overall. So this will be a -2 in its final impact. Now, this may seem odd to you to see -2, -2, and +1 and be calling that a 0 charged molecule. But remember, that's not what we're saying. We're saying that each of these atom types have this oxidation number. And if we actually want to consider how much charge they each have, we've got to multiply it by how many atoms are present.